So at the end of the previous video, I considered this example. I want to test my belief that students would spend 30 hours for an exam. But the sample mean was 31. I'd like to compare if my hypothesis is consistent with the data or my belief need to be rejected. So to do that, first, let's formulate the hypothesis in terms of parameters. The hypothesis was about the mean study hours. So I will define a random variable x as the midterm study hours for a randomly chosen student. And we'll define its expected value as the mu, which is unknown parameter. And I believe that unknown parameter equals 30. And then automatically, the alternative hypothesis becomes mu different from 30. Okay, that is set, and also already the significance level was set as 5%. And then next, we have to find the test statistic. We are going to use x bar as the sample, x bar as the test statistic, because we are talking about the population mean in the hypothesis. And you remember the best point estimator for the population mean is the sample mean. So the sample average is the best statistic that delivers information about the population mean, right? In the same sense, we are going to use the sample average as the test statistic. Also, another reason is because we are going to use the central limit theorem for this guy. We know x bar converges to a normal distribution, right? So we will use that theory. So we need x bar to apply that theory. Okay, here comes. By the central limit theorem, first, by the way, remember that I still believe that students spend 30 hours for the midterms. And by the central limit theorem, I know that x bar sample average follows a normal distribution, approximately normal distribution with parameter mu and sigma squared over n. We have done this many times in the previous chapters. And like my hypothesis is telling that the mean is 30. The mean is 30. I believe students spend 30 hours. And also the sample size is known. Sample size is 100. And standard deviation was estimated to be 10. So we know approximately x bars, the sampling distribution of x bar is normal. Okay, that is known. But parameters are 30, this. Right? 30 is coming from my hypothesis. 10 is coming from the calculated standard deviation. So one is from the hypothesis and the other is from the data. Then it would look like this. If my hypothesis was correct, then x bar, the sample average, would follow this distribution. So we call this the null distribution. Null distribution, if the null was correct, right? So that means if I survey 100 students, I would get results somewhere here. Most likely to see results here, but these extreme values are possible but unlikely. So there is still possibility below 26 and above 34, but they would be very unlikely. So using the same idea, I'm going to rank them from the outside in, right? the most outside values are the most unlikely outcomes. And then as it moves toward the center, which is 30, 30 is the least suspicious observation. So if I observe 30, if the survey results gave me a sample average of 30, that means my hypothesis is obviously true, right? Very strong evidence that my hypothesis is correct. But as it moves away from 30, then my hypothesis is more questionable. That is the idea. So we are going to calculate ranking from the outside in. That means now, but suppose that I observe so far, by the way, so far, I do not use the observed sample average. It is the distribution is coming from the null hypothesis. Remember, the center around 30. But we observe now here the observation kicks in, and the observation is at 31. It's not exactly 30, it's different from 30, but how far that is. So then, as I said, we are going to rank it. We are going to rank how unlikely this observation is from the outside. That is calculated this way. So remember, the most outside observations would be the least likely guys, and then count ranking from outside, and then up to your observation. So 31 and greater outcome observations would be unlikely if your hypothesis was correct. If the distribution is true, then this probability is the more unlikely observations than what you actually observed. But at the same time, don't forget the other side. The negative shock is as likely as the positive shocks, right? You have to treat them equally in this scenario. In this situation, like as you can get a positive random error, as likely you get a negative random error. So 29 is at the same ranking as 31. 29 and 31 are just different directions, but equally unlikely observations. So when you count ranking, these colored blue, light blue area is the probability of more unlikely results from the distribution. So ranking from the outside and bring that in, then here is your observation. So this the outside outcomes are more suspicious outcomes. So that is the p-value, remember? And as you can see from the picture, the p-value will be small if your observation was outside, right? If your observation was, for example, was at 32, then this area would be much smaller. So the smaller the p-value is, the more difference, the larger difference between the center and your observation, your sample average. Let's keep that in mind. And now then, we have to calculate this area, and you know how to do it. It is a normal distribution and simple. So the p-value must be calculated this way, either smaller than 29 or greater than 31, right? These are more extreme outcomes, more suspicious outcomes than what you actually observe. First, standardization. From here, it's purely technical, mechanical algebra. So standardize x bar into z using the same standardization form as we used before. And so, of course, you have to match both sides of inequality. And plug in. So the mean was 30, which is based on my belief. And the standard deviation should be divided by square root of n. And then, in the end, this probability equals probability z smaller than -1 or z greater than 1. If you calculate that on Excel, you will get 31.731%. So this is if you rank from the if you rank the outcomes from the most unlikely or most suspicious to the least, then your observation 31 would be top 31%, right? 31.731%. So it's like a slightly above the average, average. So standardization is based on the null distribution, as we discussed earlier, and in this derivation, almost always you are going to see the standardization process. We are going to define the standardized sample average as the t-statistic. So this t-statistic is based on the student's t-distribution that I mentioned at the end of the earlier chapter. But we don't use student t-distribution, but still the name remains t-statistic. So there is nothing special. Just the standardized sample mean is the t-statistic. In other words, I would interpret it this way. 30 is what you believed, and 31 is what you observed. So 31 minus 30 is the difference between your belief and your data. And they are standardized by the standard deviation, right? Sampling deviation, standard error. So this is a kind of, you can interpret this as the standardized difference between your belief and the data, right? That's more intuitive. Then of course, you can say that the larger the t-statistic is, the more difference between your belief and the data. So less consistency. And then based on the t-statistic, you just calculate the p-value from the t-statistic, right? You can just calculate it this way in the end. Anyhow, this is just two-step approach of like this one-step derivation, right? Anyhow, standardize and then apply normal distribution. Same thing. Standardize, apply standard normal distribution. So same thing. So then what we learned is 31% is the p-value. So it is top 31% suspicious outcome. But your cutoff was 5%. You are going to reject only 5%. That means 31% will not be rejected. You are going to reject from 0 to 5%. So 31 is safe. So you are not rejecting the null hypothesis. That means my belief that students spend 30 hours is accepted, is not rejected, right? So 31, so the observation was different because of a random error, which is possible, right? So in general, we can generalize the same framework again. So in general, you can write it this way. The null hypothesis, say the null hypothesis is about the population mean equals to a specific value of mu0. So you choose, like in our previous example, it was 30. I chose it as 30, I believe mu equals 30. And the significance level is chosen as alpha. It's your choice. And from the data, you need to calculate the sample average, standard deviation, sample size n. Exactly same guys as we used in the confidence interval, right? So almost always you get them and you know how to calculate them, right? Then you are ready. So these are all you need. Then remember, under the null hypothesis, if the null hypothesis was true, we know that the sampling distribution of the sample average is approximately normal with mean from the null hypothesis and the variance from the data. Sampling distribution of the sampling distribution theory by the center limit theorem. And we define the t-statistic, which internalizes the standardization process. T-statistic takes this form, and the p-value after the standardization apply standard normal distribution probability. And when you calculate the p-value, don't forget you have to calculate the positive side and the negative side at the same time. Both sides are equally unlikely, so you calculate them. By the way, I take absolute value because if this t-statistic could be negative, but then make it positive and then put negative again. So mathematically, you need an absolute value. So now let me do some exercise. I will change the hypothesis to this. So suppose that you are going to study, say, I believe you spend 50 hours for the final exam, say. So like that is my belief. So I believe that the population mean of students study hours in the final period is 50 hours. And versus alternative hypothesis that the mean is not 50. And I surveyed 100 random students and I found the sample average of 56 and the standard deviation is 20. In this case, so this is all the information you need to apply the method, right? In the end, the derivation and the idea underlying concept is quite confusing, but in the end, the application is pretty simple. So first, find the t-statistic. You may go back to the previous pages to see the formula for the t-statistic. The idea is we are looking for the standardized difference between your observation and your belief, right? It should be easy enough to calculate. It's a standardization. So your belief is 50 hours, your observation is 56 hours. So the difference is plus 6, and you standardize it. Standardize using the standard deviation divided by square root of n, because we are thinking of sampling distribution. So in the end, the t-statistic, the standardized difference is now 3. Now you put this into the standard normal distribution. So you have to calculate probability outside 3, which includes smaller than minus 3. So greater than plus 3 or smaller than minus 3. And calculate the p-value by yourself. So of course you need a calculator or Excel. So I'm going to stop this video here. So find the p-value and then start the next video. See you there. Bye.